The consideration of all the propagation factors can be very complex in a real environment, especially because there are many factors, and then of course because many times we don't exactly know what is the exact situation of all the buildings, obstacles, characteristics of the materials, and so on. This is why people have developed what we know as empirical models. What is an empirical model? Well, an empirical model is something that is derived from measurements and provide expressions for the average value of the space propagation losses. One of the most known is the Okumura-Hata model, which was developed from measurements done in Tokyo, and from that a very well-known empirical model was developed. Now, the Okumura-Hata model is based on measurements and is actually limited to this frequency range from 100 MHz to 1500 MHz, with given a certain antenna height, an antenna height from 1 to 10 meters, the mobile station and the base station antenna from 30 to 20 meters. And it is defined for different environments, what is known as a dense urban city, low density urban or rural environment. And they give the propagation losses expressed in dBs as certain coefficients, A, B, and R is the distance measured in kilometers. And for each one of those different environments, well, we have to compute the value of A, given those expressions here that depend on the frequency, the height of the antennas, and so on. So actually, well, that gives us a certain model that if we plot it, we obtain things like this. This is the application of the Okumura-Hata model at a frequency of 950 MHz, considering a base station that has a height of 30 meters and the mobile height is 2 meters. And here we are comparing free space propagation losses, which is the purple line, with the Okumura-Hata model for different environments, urban, rural, or dense urban. Actually, you can see that the two urban models, either large city or medium small city, in this case they're exactly the same. So what can we observe? Well, we can observe two things essentially. Now that the slope of those losses is higher than the slope that would be predicted by the free space model, and notice that, for instance, if we look at the difference between the free space propagation losses and the Okumura-Hata model, well, we essentially have like 100 dBs additional losses. So how is this value obtained? Well, as I said before, this is essentially done from measurements. Measurements done in different cities and adjusting them to the model. That was the first model, and now you can find different models based on the same principle that extend to different geographic environments, or even extend the range of those models to higher frequency range. Okay? But the basic is that those empirical models, actually, given the complex situations that we can encounter, we are able to use them to have at least an approximation of what would be the expected value of the propagation losses that we would encounter in a certain environment. So far, we have been talking, essentially focusing on attenuation and the effects that we have on the signal attenuation of the different propagation phenomena. It is also important to take into account or to consider that there are other phenomena that have to be considered and that can be a problem to establish a right communication link. For instance, one of them can be time delay spread. Imagine the case of reflection. So far we have been concerned on modeling reflection as a cause of attenuation. But imagine that I have a transmitter and a receiver, I have a direct ray, and I have the reflected ray, both of them reaching the receiver. Well, we have seen that that can cause a certain interference, constructive or destructive, but it is also true that there is a delay. The reflected ray reaches the receiving antenna with a larger delay than the direct ray. Now, that causes what is known also as a time delay spread. That is that the received signals have a certain delay that is not a single delay but has a certain spread, a certain magnitude that spreads over time. Imagine that this time delay spread is comparable to the symbol rate. Well, if that's comparable to the symbol rate, then what we have is, in addition to potential attenuation, that can be a sort of intersymbolic interference. Symbols will be mixed together, and I will have this intersymbolic interference. So that's another parameter that usually has to be taken into account when we consider propagation. It is not the only one. For instance, in a moving environment, rays reaching the receiver can have different frequency Doppler shift because, different objects in the environment are moving at different velocities. Then I can have what is known as a Doppler spread. That is, that the received signal has a frequency spread that also may limit the performance of the system. So this is just to mention that not only attenuation is important in assessing the performance of a radio communication system, but also those factors have also to be considered, and to be considered how they appear in our propagation environment. So to summarize this unit, just to say that propagation in real-world environments requires to consider different phenomena. We have seen reflection, diffraction, atmospheric effects. Now, due to the complexity of those urban environments and the incomplete knowledge that we have of the specific characteristics has led to the development of empirical models. And also, my last remark is to say that signal attenuation is not the only important factor that can limit the performance of a radio communication channel. Time delay spread or Doppler frequency spread can occur in a multipath environment, and they can also be a limiting factor that has to be taken into account.